Now we want to look at derivatives of logarithmic functions. Now first, let's remind ourselves about a little bit about logarithmic functions. A logarithmic function with a base a is read y equals log base a of x, and it is the inverse of the base a exponential function, y equals a to the x. In other words, if you switch your x and your y for your exponential function, x's and y's, you will have your logarithmic function. Now here are some examples. We have y equals 2 to the x and y equals log base 2 to the x. You'll notice the properties of inverses. Here we have the point 1, 0. Here we have the point 0, 1. Here we have the point 4, 2. Here we have the point 2, 4. So your x's and y's just switch themselves. And you'll notice that it is symmetrical about the line y equals x. Now, ln of x is a special case. ln is our natural logarithm. It is the logarithm we have when e is our base. This is the same as having log base e of x. And we write it in the simpler form as natural log of x. And the natural log of e is 1. Because remember, when you are computing logs, I'm saying here's the base is e. E to what power gives me e? And that's e to the first power. Another logarithm you need to be familiar with, in case you've forgotten, is that if you have just log of x with no base, remember that that is the same as log base 10 of x. We call this the common log, and we call ln of x the natural log. You need to refamiliarize yourself with some of the properties of logarithms: the product rule, quotient rule, reciprocal rule, and power rule of logarithms. Now we're going to use these in the next recording, these four, in order to be able to do something called logarithmic differentiation. We're able to take very complex functions and find their derivatives using logarithms. So the product rule says the log of a product is the sum of the logs. The quotient rule says the log of a quotient is the difference of the logs. The reciprocal rule says the log of 1 over a is the opposite of the log of a. And the power rule says the log of x to the y power is y times the log of x. Here are some other inverse properties. Since a and log a are inverses of each other, a to the log base a of x is x, and log base a of a to the x is x. In base e, e to the natural log of x is x, and the natural log of e to the x is x. So those are some rules that you need to refamiliarize yourself with. Okay, here's a couple more rules that you may see at some point. A to the x is the same as e to the x natural log of x. And the change of base formula, remember that allows us to change from any base to another base. Now this is log base a of x is the natural log of x divided by the natural log of a. If you've used a TI-83 or 84 calculator very much, you know that you cannot take the log base 2 of a number, or the log base 3 of a number, or the log base 4 of a number directly with that calculator. We have to use a change of base. So for example, if I want to find the log base 2 of 6, I will do natural log of 6 divided by natural log of 2, which is the base. And that will allow us to be able to use our calculator. So that is one place where we use the change of basis, just to be able to estimate logarithmic values with our calculator. Now let's get into the actual derivative rules. If we take the derivative of the natural log of u, that is 1 over u times du dx. Now that is a composite function, so that is actually the chain rule. If we take the natural log of a function, that's 1 divided by the function times the function's derivative. Notice it says u is greater than 0. Remember that when we deal with logarithms, we have to take the logarithm of a number greater than 0. Now for this function, if we put absolute values around the x, then we can use any x value with the exception of 0. We cannot take the natural log of 0. We cannot take the natural log of a negative number. But when we use the absolute values, that makes the negative number positive. So if I do that natural log of the absolute value of -2, that's actually the natural log of 2. Now let's apply those rules to this problem. We want to find the derivative of the natural log of x squared plus 3x. Well, what our rule tells us is we have 1 over u, so that's 1 over x squared plus 3, times the derivative of the inside function. So the derivative of x squared plus 3. So we have a composite function. Natural logs are outside functions. So when we apply the natural log rule, that gives us 1 divided by x squared plus 3. And then we take the derivative of the inside function. So that's 1 over x squared plus 3 times the derivative of x squared is 2x. The derivative of 3 is 0. So this is just 2x divided by x squared plus 3. So the derivative of the natural log of x squared plus 3 is 2x divided by x squared plus 3. Now you'll remember in a previous recording we looked at the derivative of e to the x, and we said the derivative of e to the x was e to the x. Now we're going to look at different bases. If our base is a, then the derivative of a to the u is a to the u times the natural log of a times the derivative of u with respect to x. Now what that means for this particular problem, we have the derivative of 5 to the square root of x. So we have a composite function. Our outside function is the 5 to a power. So when we apply that rule for the derivative, that is 5 to the square root of x. Now, since we have a different base other than e, we have to multiply that by the natural log of 5. That's what our rule tells us here. Now, the reason we didn't have to do that for e is that the natural log of e is 1. Okay, so we left that part out. But then we have to multiply by the derivative of the square root of x. So this is a composite function. We look at what would we do if we just had 5 to the x. Well, if we just had 5 to the x, it would be 5 to the x natural log of 5. Since it's 5 to the square root of x, we have to also take the derivative of the square root of x. So I have 5 to the square root of x times natural log of 5 times. Now remember that the square root of x is x to the 1/2, so we're going to apply the power rule again. That is 1/2 x to the negative 1/2. Now we can write this in different ways. If I want to use positive exponents, I can say, okay, I got natural log of 5 in the numerator. I'm going to put parentheses around that, times 5 to the square root of x. Both of those would go in the numerator. Now I put parentheses so that it wouldn't look like the 5s are being multiplied together. In the denominator we'd have the 2, and when we bring the x to the 1/2 down to the bottom to make it positive, we'll do square root of x. So that would be the derivative of 5 to the square root of x. Now one other rule we want to look at here, what do we do if we have the derivative of the log base a of u? That will be 1 divided by u times natural log of a times the derivative of u. So if I have log base 2 of 5x, that is going to be 1 divided by, in this case our u is 5x, times the natural log of our base, which is 2, and then we're going to multiply that by the derivative of our 5x. So I have 1 divided by 5x natural log of 2 times the derivative of 5x is 5. So that is 5 divided by 5x natural log of 2. Now notice I have 5 on top and bottom. 5 goes into 5 one time and into 5 one time. So that's 1 divided by x natural log of 2. Or, if you prefer, you can put the natural log of 2 first. If you do that, I would suggest you put parentheses around it so that it doesn't look like the natural log of 2x, and make it natural log of 2 in parentheses times x.